Welcome! In this presentation, we are going to talk about the cycle of math anxiety and how we can break it. We're going to start with the definition of math anxiety and then move on to causes and interventions. Then we're going to home in on math fact fluency, which is probably the most important first step we can take to prevent math anxiety. Math anxiety is a feeling of tension and anxiety that interferes with the manipulation of numbers and the solving of mathematical problems in ordinary life and academic situations. Math anxiety is correlated with low math performance and low math self-concept, as well as avoidance behaviors. Also, low enjoyment and motivation in math. At first, it was believed that young children didn't experience math anxiety, but more recent research has discovered that math anxiety starts in very young children, possibly on day 1 of kindergarten. Let's talk about some of the causes of math anxiety. Does math anxiety cause low mathematical ability, or does low mathematical ability cause math anxiety? This is one of the first questions asked since math anxiety was defined in the 1950s. And it's been under debate ever since. Researchers' conclusions about the direction of causality depend a lot on what they are studying and what type of research they are doing. In the disruption model, math anxiety causes poor performance. This is a short-term effect and easy to observe, and for this reason, researchers originally concluded that math anxiety causes poor performance. In the deficit model, poor performance leads to math anxiety. This takes place over time, so it takes a longitudinal study to see it. But the truth is, it's a cycle. Both pathways are valid. Instead of 2 models, we have 2 pathways in 1 model. We'll start with the disruption pathway. The disruption pathway involves working memory. The disruption of working memory occurs in any counting or math-related task that relies substantially on working memory. Specifically procedural tasks such as keeping track in a multi-step problem. This includes things like multi-step computations, sequencing of mental procedures, mental lookup of formulas and equations, or using strategies for doing computation. This is most of the math after 4th grade, but it also includes a lot of the work in 3rd and 4th grade. Even college students often use counting strategies instead of direct recall as their normal method of doing subtraction. This is using strategies for doing computation. It leads to higher response times and more errors. That was the cognitive part of the disruption pathway. Cognitive anxiety involves negative thoughts. Next, we're going to talk about affective anxiety, by which we mean negative emotions. First, we'll talk about avoidance behaviors. Students with high math anxiety hurry through math tasks, but that causes very low accuracy and less learning is taking place. This is an example of short-term avoidance. Students with high math anxiety also have a hard time paying attention in math class. This is an example of a midterm avoidance behavior. Since they're not paying attention, they're learning less, and this leads to reduced math performance. Lastly, students with high math anxiety take fewer math courses in college and high school, and they choose majors and careers that require less mathematics. As a result, once they are in a position to choose their coursework, they limit their opportunities to learn math by avoiding math classes altogether, which is a long-term avoidance behavior. For a while, people thought that this was a one-way street due to the lack of longitudinal data. So now let's talk about the deficit pathway in which poor performance leads to math anxiety. Longitudinal studies are important because you can't detect the deficit pathway without them. Here's one really important longitudinal study that was published in 2003. It spanned 6 years worth of following students from grades 6 through 12. There were over 3,000 students involved, and the students came from more than 50 schools. And what they found was that the deficit pathway is 2 to 16 times as powerful as the disruption pathway. Or in other words, the researchers said, by comparison, prior mathematics anxiety hardly related to later mathematics achievement in comparison to mathematics achievement and causing later mathematics anxiety. So, math anxiety is a cycle, but the deficit pathway in which low ability leads to anxiety is much more significant than the disruption pathway. But what is the mechanism for the deficit pathway? One piece of it is self-perception. Students' self-perception of their ability is a stronger predictor of math anxiety than their actual ability. So now we have a cycle that looks like this, with perception of low achievement being a stop along the way from low achievement to anxiety. And students' beliefs are very important. Students who have an entity-oriented motivational framework believe that their intelligence is fixed. They prefer easy tasks that allow them to succeed, or performance goals. On the other hand, students with an incremental motivational framework believe that intelligence can change through effort, and so they prefer challenging tasks that help them to grow, or growth goals. Performance goals leave a child vulnerable to feeling powerless when setbacks occur, leading to anxiety. As with other pathways in the deficit model, the path leading from low achievement toward anxiety is more powerful by a lot than the path leading from anxiety to low achievement. In this pathway, prior negative experiences with math create a belief that math-related tasks are not within the student's control, which leads to anxiety in math or numbers-related situations. There's a large body of work that finds that the perceived inability to personally influence actions and outcomes in the environment are the major determinants of anxiety. So if you slept through the entire beginning of this presentation, here's what I want you to take away from it so far. The most powerful pathway is from low ability or low performance to a low perception of ability, and from there to low self-efficacy, and then to low anxiety, to high anxiety. And this is our best opportunity to intervene. Here are a few other influences that contribute to the cycle. One is genetics. Another big one is social influence, and this mostly comes from parents and teachers. It's especially powerful when there are female students of female teachers. And our pedagogical practices also contribute to students' levels of achievement, which of course starts the whole cycle. And so now our cycle looks like this. Now let's talk about some interventions. In this diagram now, I have colored green all the arrows that represent paths where we can intervene in the cycle of math anxiety. Black arrows are things that we can't really do anything about, but as you can see, there are a lot of things that we can do. We're going to start with step 1 at ineffective pedagogy. It's important in our pedagogy that we use practices that emphasize basic numeracy and automaticity. Almost every researcher that I have studied in my research on math anxiety has recommended that teachers focus on these concepts, numeracy and automaticity, as a start for helping students both to prevent math anxiety and to deal with math anxiety that has already developed. Along with this, we want to emphasize conceptual understanding of mathematics, and we want to allow students to go at a pace that gives them enough time to develop this conceptual understanding before they move on. Additionally, we want to watch vigilantly for mathematics achievement deficits and respond to them immediately before the student has a chance to begin to feel like they don't have any power over the situation. As far as the perception of low achievement, we want to avoid comparisons. This includes grades and competitions between students. We often think that a little competition will motivate students, but the truth is it motivates those who are able to succeed, and it has the opposite effect on those students who feel like they can't succeed. So we want to avoid competition in general. We want to avoid verbal commentary, like making comments that tell the students which students we believe are doing better than others, and charts that have the same effect. We want to help the students to focus on mastery of the content, and we want to help them to develop the ability to recognize their own progress, because recognizing their own progress is going to allow them to develop more self-efficacy and more of a belief that they have power to change their ability. We also want to work on self-efficacy with our students. We want to help them develop a growth mindset. We want to say out loud that all students can learn math, so that they are hearing that from us and they believe that that is a general perception, that everybody can learn math. We don't want to have any negative stereotypes, and we want to actively combat them when we can. In addition, we also want to acknowledge when students have failures and encourage them to make additional effort and help them to recognize that effort will help them to get past the difficult parts. Here is a chart of intervention strategies that correspond to the whole cycle of math anxiety. Because this is a shorter presentation, I'm not going to go through all the other steps, but what I mainly want to focus on is this, that the most important interventions are along the deficit pathway, meaning from low mathematical ability to math anxiety. The most important interventions are in our pedagogy and in helping students' perceptions of themselves and in helping them to develop self-efficacy. From here, we're going to transition to math fact fluency, which is one of the elements of basic numeracy. It is essential for developing conceptual understanding of math concepts as well. And as such, it's very important in helping students to prevent and deal with math anxiety. Fact fluency involves both a conceptual understanding of how numbers work together and the ability to recall basic math facts directly from memory, which is known as automaticity. Automaticity means direct recall from memory with no counting strategies, songs, or other mnemonic devices. Unfortunately, few people know how to teach direct recall, and there are few tools available that do it well. To address that problem, I dug into the research to find out how we should be teaching direct recall. You'll be glad to know that it is possible, and here's what I learned. Teaching automaticity is completely different from teaching conceptual understanding of math facts. A lot of what we do in teaching automaticity is the opposite of what we did when we were teaching conceptual understanding. For starters, we need to provide the students with scaffolded learning that targets one new math fact at a time, helping them to develop automaticity in that one math fact while ignoring all of the rest. After teaching a new fact, we need to review the math facts they've already learned to keep them fresh, but we don't ask them to answer any math facts that they haven't had a chance to learn yet. That causes anxiety. That means that we just don't work on the math facts that we haven't taught yet. In teaching automaticity, we need a controlled response time. That means that there is a limit on the time students have to answer an individual math fact. When they can't answer in time, we give them the answer and let them try again. To be effective, the controlled response time needs to adapt to the ability of the student, and we need to work it down to less than 1 second. It is sometimes a little frustrating, and that's actually the magic ingredient. That little bit of annoyance is what makes our brains transfer that information into memory for direct recall. Otherwise, our brains would be happy to just keep calculating the answer each time we need it. Without a controlled response time, we do not develop automaticity. We need to separate math facts with a common operand, such as 2 times 6 and 2 times 4, because they each have the operand 2 in them. This causes the answers to get conflated in memory. Very importantly, we need to practice every day. Memory degrades a lot in 24 hours, so if students don't practice every day, they won't be able to retain their newly learned math facts. As I mentioned earlier, many of these principles are different from what we do when we're teaching conceptual understanding of the math facts. They also require a lot of adaptation to individual students, and that makes it hard to implement these principles in the classroom. It also means that flashcards, or software that works like flashcards, are the exact opposite of what we need for teaching math fact automaticity, because flashcards and similar things violate all of these principles. So do worksheets, whether they're timed or untimed. If you want to learn more about these research principles, I have created some 3-minute videos that explain each principle. I'll give you this link again at the end of the presentation. Since all of these principles require careful adaptation to each student, I created Everybody Math to implement them for you. The one exception that I could not implement for you is everyday practice, and that's still something that teachers and parents need to make time for. But I did build in detailed reporting to help you with that part of it. Let's imagine Anna is logging into Everybody Math today. The first thing we'll do is review math facts that she has learned in the last few days. These are shown as purple on her chart. If Anna doesn't remember one of her recently learned math facts, such as 4 times 9 equals 36, we'll set that aside for more scaffolded learning today. This way we can be sure we aren't introducing new math facts when she hasn't learned the old ones yet. Next, we'll pretest Anna on a few math facts so that she can skip scaffolded learning on those she already knows. We don't want to cause anxiety by asking her to answer any math facts that she hasn't had a chance to learn, so she'll have a skip button during the pretest. Next, we dive into the scaffolded learning. This is where we'll spend the bulk of our time. We'll teach Anna 1 or 2 new math facts so that she can answer each of them in less than 1 second, 3 times in a row, even with other math facts in between. Since Anna needed more work on 4 times 9, we'll make that one of our scaffolded math facts today. We'll also choose a new one that she hasn't learned yet, like 6 times 3. Last of all, we'll review math facts that Anna already knows well. These are blue on her chart. Reviewing them frequently will help Anna to stay automatic in these facts after she has learned them. Everybody Math gives you a lot of tools to help you guide your students. On your homepage, you can see a summary of your students' fluency in each operation, as well as the last day each student completed a practice. On the My Class page, you can see information about individual students and whether they are practicing. You can also select one student to see their fluency level in each math fact, as well as their progress over time. You can set learning objectives if there are certain math facts that you want your students to learn soon. Everybody Math is effective at teaching automaticity, provided the students are given time to complete a learning session each day. One teacher said, "The difference is amazing. The students who have been using Everybody Math finish their IXL lessons so fast because they know their math facts and it makes a huge difference." A parent told me, "My daughter was in the resource program last year to help her with her math skills. We had her do Everybody Math consistently all summer. When they tested her at the beginning of this year for Math Resource, she didn't even qualify. She was caught up to grade level. We are very pleased with this program. Now we've got everybody on it just to boost their math skills. We love this program." Here are a few resources you can use to learn more. The first one is just a link to the Everybody Math application, which is a web-based application. If you create a teacher account there will be an option in your teacher dashboard for you to be a student, and in that view you can just do everything that a student would do, and everything looks the same way that it would look for your students. So you can try it out from the student's perspective. In the second link there's just a short video where you can kind of see the app in action and see some of the summary of how it works. In the third link, those are the short videos to different elements of the research. And in the fourth link, you can send us a little information about yourself if you'd like to ask questions, get more information, be part of a free trial, or be part of a study that we'll be doing on math anxiety and math fact fluency. You can also just email me directly at melanie@everybodymath.com.